Well, let's see if we can't now apply that to our pendulum. Our pendulum just had alpha equals 1. We didn't have a coefficient there at all. And we didn't even have an x prime term, which meant beta was 0. And our gamma term was the gravitational constant divided by L, which we also called k squared. So if we make those substitution, this becomes our second order differential equation that drives that pendulum. Let's do just a little more simplifications here. First of all, let's rename x of t, and we're just going to call it x sub I. I is going to represent a time index. If we move one value bigger, we're going to call it x sub I plus 1. It's just the next discretized value. All of these are evenly spaced. I should be able to just index them using indexes of I and get the same thing. And then this guy over here to the right is x sub I minus 1. Now looking at this, you might claim, what happened to your time variable? You know, it seems to have disappeared. You've got your x's, that represents the angles, we know that, but where's time? Well, time is represented by h, because that's a time period, and I is the discretization of time, not of the angle, but we're discretizing the time. And so each one of these x sub i's are separated by h units in time. So don't lose track of that. Now we could also simplify this even further. We could factor out the h squared, or 1 over h squared, and we end up with an h times k squared for this term here to make that work. And we're going to get rid of the 1 over h squared altogether just because it's messy. I'm going to rearrange things a little bit. I'm going to put the I minus 1 on the left. I'm going to put the I plus 1 on the right and the I in the middle just because it's going to work out a little better. And when I do that, I end up with this expression here. So I have a earliest time period sort of lagging back by one time period, the current time period I, or the angle at that time period times some coefficient, and then we have the next angle position. So what can we do now with this? Well, we have a nice structured equation that relate all of the angles in the entire half cycle of this pendulum together through this linear relationship. This is a linear equation. Well, it's actually more than a linear equation. It's many, because the i's can take on values anywhere from x or I from 0 up to n. But let's just start with I equals 1 and see what we really have here. Well, if I is equal to 1, so it's one position past that initial value, we end up with x0, the initial condition, plus this coefficient that's in the parentheses times x1 plus x2. That has to be equal to 0. So we have one equation and 3 unknowns. Okay, so that's well, okay, maybe I can get more equations. Let's let I equal to 2. So we have x1 plus the same coefficient times x2 plus x3 is equal to 0. Well, I just got a second equation, but I have 4 unknowns. Now that's kind of looking like a moving target. That's going to continue. If I let I equal to 3, we have an x2, an x3, and an x4. I've just added another variable. I have 3 equations and 5 unknowns. I'm never going to be able to solve that unless I back up and remember that every second order differential equation to get a unique solution must have 2 boundary conditions, or it must have 2 initial conditions, or it's got to have 1 boundary condition and 1 initial condition. It's got to have something to cause it to be unique. And then we have the same issue here. So we really know what they are. We know that x0 is the initial angle. We call it theta 0. So that's an equation. x0 equals theta 0. And we also know that when we went over a half a time period, that the pendulum swung to the other side and went just as far to the left as it had been to the right, which means that our x sub n, that was the end of that period, must be equal to minus theta 0. So those are two new equations that we can add, making up the deficiency, and we now have n linearly independent equations and n unknowns. And that's good news from a linear algebra point of view, because now we can go back and use our linear algebra tools to solve this. So that's very good. So just as a reminder, we haven't lost time. H is your time variable that is keeping track of the spacing between these angles, I mean the time spacing between the angles. The discretization is on time. It is not on angle. The angles are going to be varying and the spacing between angles will vary, but the times will be fixed. These equations we're looking at here only work for interior points. We're going to start calling x1 through xn minus 1 interior because they're not the boundaries. We do need x0 and x1, but we've got them. So we've really got everything that we need to solve this equation. Well, let's go back and think of this from a matrix point of view. If I lined up all of these angles from the starting theta 0 to the final minus theta 0, and they're all discretized in time, so these are the solution angles that come out of it. If I set it up as a matrix, I will get 1 times x0 plus this coefficient times x1 plus 1 times x2 is equal to 0. Well, that was my fundamental equation for I equals 1. For I equals 2, I get the exact same form, but involving x1, x2, and x3. And that also has to add up to 0. And that continues until I get to the bottom, where I have x sub n minus 2 plus the same coefficient times x sub n minus 1 times x sub n, and that also equals 0. Now, conveniently, we've left some space at the top and the bottom of this matrix, so we can define our initial conditions. So if I just put a 1 here where it's now blank, I'll end up with 1 times x0 is equal to, and I better put theta 0 up there to make that work. And at the bottom, I can put a 1 down here in the lower right-hand corner, and I'll end up with 1 times xn is equal to, and in this blank, I better put in a minus theta 0 to make this thing work. Then I have a truly tridiagonal system, and our homework that we did back in chapter 2 will be able to be used to solve this problem, and that's exactly what we're going to do in this homework. So let's think about that discretization for a moment. We know this starts off at theta 0 when time is equal to 0. We know the last angle is going to be minus theta 0 for x sub n, and we know that's going to happen at 1/2 the full cycle period. Because the cycle is the entire round trip, also called the period. Well, then we are breaking up our time periods over 1/2 t. We'll need to know what that capital T actually is to be able to solve this problem. But when we do, we end up having a complete solution to it over a half cycle. Now, if you get it over a half cycle, you can pretty much work everything else because it just goes back and forth and back and forth and back and forth. So your problem is really solved. Well, the full round trip cycle T, as you learned in Math 321, is 2 times pi times the square root of L over G. Now, we conveniently called L over G K squared, so you could call it 2 pi K. But I'm starting to get a little heartburn about what I'm telling you, and I hope you're getting a little heartburn too, because we're really cheating. We're making use of an analytic solution to help us with a numerical technique. That is too big of a crutch. We need to be able to come up with methods that answer the differential equation without knowing a thing about the solution analytically, because after all, most of our differential equations are going to be in that condition. So this is a bit cheating. That's okay, we'll cheat for a little bit. We'll even give you a homework problem where you get to use this cheating method, but then we're going to take the cheating away when we get to the next lecture. So let's try it. Let's summarize this thing. Here's your basic solutions, and in your homework, you're going to need to build that matrix that I just had a couple pages ago using this formula. So that's going to be the first thing you're going to have to do. You're going to have to divide this full period in half. So you basically have pi times the square root of L over G, and divide that into like 20 or 30 intervals. That's going to give you your H value. You'll have to use the above formula knowing that you've got to stay between 1 and n minus 1 when you're using this formula, because you're going to have a problem if you let I equal to n. You'll end up with an x of n plus 1 out here, and you don't know what that is. And the same thing's going to happen on the other side. If you try to set I equal to 0, you're going to have an x minus 1, and you're not going to know what to do with that either. So we'll limit these equations just to the interior points, but we will allow our boundary conditions to save the day, giving us the extreme points that we need so we can solve the problem. Now you're going to go back to homework 2.3b, and you're going to use that as an efficient way to solve this problem. Okay, so you have your n plus 1 equations, you have n plus 1 unknowns. Here is the matrix you're trying to create. So go ahead and set that up in MATLAB and solve it using homework 2.3b. So this is really just a summary of what I already told you, all boiled up into a nice homework assignment. It's worth 50 points. It's not nasty. It's not too hard to do. Just follow the matrix that we've already got there in the previous slide, and you should be able to answer all of these questions. Now I am asking you to answer a few other things in here, so you're going to have a little bit of a mix of write-up. You have to write the code, and then you're going to have to do the graphing, and you're going to have to tell me from that some angular velocities partway through it. And I need you to think about how you do that from the vector of solutions you get of the angular positions. So think about that. And tell me what the answer is. So this is a mix of MATLAB and some written answers with justifications based on the MATLAB results. So that's enough for now. We're going to end this section, 7.4a, and we did leave it with a very accurate, efficient way to solve this pendulum program with a bit of cheating, knowing something about the period. And the next section in 7.4b will take the cheating away and have you solve the same problem using initial conditions only and not having to make any assumptions about the solution of the pendulum, and that will finish the course.